What's up, my pre-calc people? In this video, I'm going to teach you how to crush the third free response question on this year's AP Precalculus exam. Now, on this question, you cannot use a calculator, and it is a context-based question, which means there's real-world implications to it. Now, this problem is going to be periodic in nature, which unfortunately means you are going to need trigonometry. The third free response question is going to have three sections, A, B, and C. In section A, you're going to be asked to use the scenario to fill 5 points in on a sinusoidal curve. Now, you got to be able to read the question to know exactly what you're going to fill those points in. Now, this particular section is worth 2 points. You're going to get one correct point if all of your input values are right, and you're going to get a second point if all of your output values are correct. On section B, you are going to be given a sinusoidal model. It's either going to be a cosine model or a sine model with transformations A, B, C, and D. You're then going to be asked to find the values of A, B, C, and D based on the sinusoidal curve and the points that you created. You will get 1 point if you get the A and the D value correct, and you will get a second point if you get the B and the C value correct. Section C has 2 parts asking you to focus on a particular small interval of the sinusoidal function. In part 1, you're going to be asked about how the output values are changing over this interval. Now, this particular part is actually multiple choice. The choices are either going to be that the output values are positive increasing, positive and decreasing, negative and increasing, or negative and decreasing. And you're going to analyze that particular section of the graph to make that choice. Part 2 is going to be asked about how the average rate of change is changing over this particular interval. So here we want to focus on the concavity of that particular section of the graph. If it's concave up, the rate of change is increasing, and if it's concave down, the rate of change is decreasing. All right, let's dive into a full example of exactly what this third FRQ is going to look like, and we're going to show you exactly how to solve it. So here's an example of exactly what FRQ number 3 could look like. An old mill has a water wheel that spins from the current of the river it is in. The wheel rotates in a counterclockwise direction, and it spins 1 revolution every 3 seconds. The diameter of the wheel is 30 feet. Consider point A on the edge of the wheel as shown in the diagram. When point A reaches the top of the wheel, it is at its maximum distance above the water at 26 feet. When point A is at the bottom of the wheel, it's at its lowest point 4 feet below the surface of the water. And at time t equals 0, point A is at its lowest point. So point A starts at its lowest value, which is right here, 4 feet. They're telling us 4 feet below the water. It rotates in a counterclockwise direction until it gets to the very top where it's at its highest point above the water at 26 feet. And then it continues to rotate all the way back to where it began. And that whole process takes 3 seconds to go 1 revolution. The sinusoidal function h models the distance in feet between point A and the surface of the water as a function of time in seconds. Positive values of h represent distance above the water, and negative values of h represent distances below the water. Now, the first thing I like to do once I'm done reading this problem is I like to really understand the picture. So there we have point A starting below the water. We were told that it is negative 4 feet below the water. Now, we were also told that the diameter of the wheel is 30 feet, which means the radius of the wheel is 15. So this distance all the way to here is 15 feet, and then same thing with this distance all the way to here. But we already have negative 4 below the surface of the water, which means that 11 would be above. So from the center of the wheel, we go down 11 feet to the surface of the water, then we go down 4 more feet until we get to that lowest point. Now, when we allow this wheel to rotate, I like to think about every quarter rotation. And this is going to really help you when we get to part A in a moment where we have to make a graph. So right here we start at time 0, and at time 0 we are negative 4 feet below the water, or 4 feet below the water, which is a negative value. Then after a quarter of a revolution, 1/4 of a revolution, I'm going to put 1/4 there, 1/4 of a revolution around the wheel, it is now how far above the surface of the water? Well, that's the 11 feet, because remember, when we're equal to that center or level to that center, we are at 11 feet above the water. Then we're going to go to a half a revolution. A half a revolution is the very top. I'll put a 1/2 right there. And at half a revolution, we were already told that it's 26 feet above the surface of the water. But hopefully that makes sense as to why it's 26, because we got the 15 to the center, and then we got 11 more to the actual surface of the water, which is why we're 26 feet above the water. Then we have 3/4 of a revolution. That's all the way over here, 3/4 of a revolution. And at 3/4 of a revolution, we're back equal or level to the center of the wheel, which once again puts us 11 feet above the surface of the water. And then finally, after one full revolution, all the way back, we're back to that low point, -4 or 4 feet below the water level, which is a value of -4. Now, the next thing I like to think about is the time it takes to do all of this. We know one revolution starting from A going all the way back to A is 3 seconds. So 1/4 of 3 seconds would be 3/4. So the time to get to this spot right here, 1/4 of a revolution, 1/4 of 3 seconds, is 3/4 or 0.75. So at 0.75 seconds, we're at that 11-foot mark, 11 feet above the surface of the water. Then at the very, very top, we're at a half a revolution. One revolution is 3 seconds. So half of 3 seconds is 1.5 seconds. So at 1.5 seconds, we are at that 26-foot mark, 26 feet above the water. Then at 3/4 of a revolution, which is 3/4 times 3, 3/4 times 3, that's 9/4 seconds. 9/4 is 2.25 seconds. So at 2.25 seconds, we are at 11 feet. We're back to that 11 feet distance from the water. And then finally, after 3 full seconds, we're back right to where we began. Now, we already know ahead of time exactly what section A is going to ask us. It's going to ask us to track those main points as we rotate around. So that's exactly what we're going to have to do. So really getting a good grasp of all of that that's taking place is going to really, really, really help you. Now, I want to say one really important thing here before we move on, because again, I don't know exactly what the test is going to say, but in this particular problem, we said that it went one revolution in 3 seconds. Which is exactly one full period. One revolution, 3 seconds. How long does it go one period? Well, 3 seconds. That's easy. But imagine if a problem said something along the lines of this. Hey, we could do 5 revolutions in 1 second. Now, that means it's with the wheel spinning really, really quickly, because in 1 second, it goes around 5 times. So in that situation, be very careful. The period is not 5. The period is 1/5. Meaning that it takes 1/5 of a second to go one revolution. So the problem I created is like a lot of the practice problems I've seen, where it's quite simple. One revolution, 3 seconds. We know to start to the end, it takes 3 seconds. But be careful if we were told something about 5 revolutions or a larger amount of revolutions per 1 second. You do have to do 1/5 of a second to go all the way around. So really think about that, because that's definitely going to affect your answers. Now, that's not how this problem was set up, but you just never know what's going to be on the exam. All right, so now we want to actually track all those points. Now, here's the most important thing, is where do we start? Because this is what the graph is going to look like on your AP exam. And a lot of kids want to always start at F, because F's the first point, so let's start at F. But no, we have to start where they told us to start. And remember, it said that we start at our lowest point. So we could start at J, because J is the lowest point, but J is also in the middle. We want to have the start be at the beginning. So for this particular problem, the way it's set up, it's really important for me to think about bringing the curve down to here. Even though that was not given nor asked, it's important that we start there. So that's where we're going to start at 0 seconds. We know that we're at -4 feet, or 4 feet below the surface of the water, which is a negative value. Then the next thing I like to do is think about where we're going to go back to that point. So if we do one full revolution, we're going to go all the way to our max and back down to our min. There's one full revolution, and we know that that takes 3 seconds. So now point J should be at 3 seconds, and we're right back to that -4. And if we were to do another revolution, which would take us all the way to here, that would be 6 seconds, another 3 seconds, and we'd be back to that -4. But again, that point wasn't asked, but it's really important to understand what's happening here. Now, we also have to find the next couple points. So here's what I think about. I think about, okay, where am I at my max? My max is 26 feet. When I'm at that highest point, we already said in our picture that we're 26 feet above the surface of the water. Whether I'm at point F or I'm at point P, that output is 26 feet. But what about the time to get there? Well, F is a half a revolution. Right? You can actually see it in my picture here. It takes half of a revolution to get to that maximum value. But we also saw in our picture here that to get to that top value, it takes a half revolution. But one revolution is 3 seconds, so half of 3 seconds is 1.5 seconds. So that's where I get that this is 1.5 seconds, because it's half of that full period, which is 3 seconds. So that means that at 4.5 seconds, I'm going to be at that p-value because that would be a half a revolution. Half a revolution is 1.5 seconds. But if I'm starting at 3 for my next cycle, my next period, 3 plus 1.5, it takes me to that 4.5. Now, what about my quarter point? Well, that would be this first point right here where I'm at my first quarter. 1/4 of a revolution, 1/4 of 3 is 0.75. So 0.75 seconds, we are 11 feet above the surface of the water. Again, go back to the picture, right? That's right here. At 1/4 of a revolution, 0.75 seconds, we were 11 feet above the surface of the water. Now again, that point wasn't asked, but it's important to really track these points. Then point G is my 3/4 point. It's 3/4 around the circle. 3/4 of 3 is 9/4 or 2.25 seconds. Now you are allowed to have fractions here, or you could have the decimal. So if you put a 9/4 there, it's totally correct, or you could put the 2.25 seconds. And at 2.25 seconds, I'm back to that 11-foot mark. Let me show you that in my picture. That would be right here. Remember, that's 3/4 of a revolution. Revolution's 3 seconds. 3/4 of 3 is 2.25 seconds, and I'll be 11 feet above the surface of the water. So hopefully this is all making a lot of sense as we track it. Then we're going to continue to move on another revolution. So that's going to be, another quarter revolution, which is another 0.75 seconds. So that's going to be 3.75 seconds. Again, 1/4 of a revolution is, I can't keep saying it because I really want you to hear it. It's 1/4 of 3 seconds, which is 3/4 or 0.75 seconds. And that's going to bring us back to that 11-foot mark. And that's going to be that midline, which we're going to address next. So it's important that you understand this graph. So now listen, a couple of adjustments we can make. Like I could start here, like this point could have been my 0, but then I'm going to be going backwards to find F and G, and they would need to be negative times, which, well, time really can't be negative. Now, I honestly don't know if the graders would grade that as correct or incorrect. I'm guessing they would not, but I mean, it would still be correct in terms, it wouldn't be correct in the real world problem, at least with context, but it would make sense graphically speaking. So hopefully that all makes sense. But I want to note that this problem, the problem that I created for this video, I started at the lowest point. If the graph or if the problem said, no, point A actually starts at its highest point. Okay, well then when I would go to my graph, then F would be my starting point at its highest point. That would be times 0. And at times 0, I'd be 26 feet above the water. And then my full cycle, 3 seconds, would be all the way back to point P, where I'm now back to that max. So again, it's really important that you understand where you start. You could also have a starting point of like your quarter point right here. Like we say, we're going to start at this value that's level to the surface of the water. Well, then that would now be our starting point. And then one full revolution, taking 3 seconds, would get us back to that point, 11 feet above the surface of the water. Now, I will be honest, all the practice questions I've seen so far either have her starting you at that lowest point or they have you starting at that highest point. But keep in mind that that's definitely going to determine how you make your graph. So here's a nice final picture with all typed up instead of my messy handwriting of those 5 points, F, G, J, K, and P. All right, now part B is going to ask us to actually model this. So it's going to say model the function D can be modeled with this cosine sinusoidal curve, A cosine of B times T plus C plus D. And they want you to actually find the values of A, B, C, and D. All right, let's begin. Now, A is the amplitude. Well, not always. The absolute value of A is the amplitude. We should say that. And all we got to do is go back to our graph here, and we see that the amplitude is going to be how far you are above or below the midline. So the midline is at 11. We could go up 15 to get to that 26, or we can go down 15 to get that -4. So my A value is definitely going to be 15. Now, it could be negative or it could be positive, and I'll get to that just in 1 second. Now, what about the D value? The D value is going to be the midline. The midline is clearly 11 because the graph has that midline right here in the middle of 11. That's pretty simple. Now, those are vertical transformations, right? Those are things that happen vertically. The amplitude getting stretched up 15, down 15 from that midline, and also the idea of the midline moving the whole graph up 11. But it's really important that you understand where you're starting. So when you think about making this cosine graph, where do you want to start? Well, it's important that you remember that cosine curves do not start on the midline. Cosine curves either start at their highest point or they can start at their lowest point. So if I want f to be my starting point, then I'm going to start at f, that's above, that's at my max, and I'm going to go all the way down, and then I'm going to go back to that same starting point at that maximum. There's one full period. 1.5 to 4.5 is a total period of 3 seconds. So if that's the graph I want to use, then my A value will be negative because, well, gosh, I can't believe I said that. Forget I said that. My A value will be positive 15. Because when you start at the top, that's what traditional cosine does. If you wanted to start at the minimum, then you would need a negative on that A value, because if you start at your minimum, that's going to be a reflection across that midline. So keep in mind that A can be positive or negative, but in this situation, I want it to be positive based on how I shaded that blue section there. Now, what about the B value? This, for some kids, is the trickiest to find. The B value is not your period. 2 pi divided by b is your period. Now, the period is how long it takes to go from your max to your max or your min to your min, whatever you're going to view as one full period. So from my max to my next max is a total of 3 seconds, which I already knew that was my period, but now I have to solve for my b value. So I'm going to multiply the b over, and then now I'm going to solve for b, dividing by both sides by 3. So I get a b value of 2 pi over 3. For my b value. So there's my b value, 2 pi over 3. Now the c value is where so many students struggle. Traditionally, cosine starts on the y-axis at an x value of 0. It goes down to its min, back to its max. There's a traditional cosine curve. Now, I'm not starting at 0. We're starting where I decided to start at 1.5. Okay, so that means I'm starting to the right 1.5. I'm supposed to be starting at 0, but the way I chose my graph, I'm right 1.5. That means my C value needs to be negative 1.5. Because for me to move my graph horizontal translation to the right, that would be a negative C value. A positive C value moves you left. I want to move to the right. So there is one possible outcome for my A, my D, my B, and my C. A and D go together because they're vertical. B and C go together because they're horizontal. Now, what I think it's really important to do in this video, because this is a video to help you do really, really well in the FRQs, is to show you that there are actual other possibilities. It all depends where you want to start. So what I always tell kids, when you're going to create a function, finding your A, B, C, and D values, you need to graph what you visualize as one full period. So what if I visualize one full period as J back to its min? That would be totally fine. That is one full period of a cosine graph. Totally allowed. Now, what does not change is the fact that the amplitude is 15. Definitely still 15. What also does not change is that the D value is 11. What also does not change is my B value is the value that helps me find the period, which in this case is going to be 2 pi over 3. But if that's where I'm going to start, down at my min, I first need to put a negative on my A because that's a reflection. Traditionally, cosine starts at its max, but I'm starting at the min, so it's going to be a negative there. And the C value is where that starts. Where does the section of the graph that you're building start? Well, this graph starts at 3. Again, traditionally cosine starts at 0, but I'm starting to the right 3, so I need a negative 3 for my C value. So there's another set of possible answers for A, D, B, and C. And you know what? We're here, might as well do one more. I could also start down here. Now, I know that that's not shown, but you could easily add that section of the graph, and there is another cosine curve. All right, once again, what does not change? My A value is 15. My D value is the 11. My B value is the 2 pi over 3. But this time, I'm starting down here at 0. Well, since I'm starting at the min, I do need to have a negative on my A value for that reflection. But now my C value would be 0 because I'm starting at 0, and that's traditionally where cosine likes to start. And if you start at 0, you don't need a translation left or right at all. So that's a third possible outcome that you could have for this particular question and still get it fully correct. Now, one more thing that could happen that could totally throw you off is they might ask you to use a sine curve instead of a cosine curve. Every sinusoidal curve can be written as a sine or a cosine curve. So again, B careful. Read. They want me to create a sine curve. Now, sine starts at its midline. It does not start at its max or min. It starts at its midline. So you might say, oh, I see a sine curve right here, starting at its midline G, going down and going back up and then back to the midline. That would be a sine curve. All right, what does not change? Well, the amplitude is still how much we go up and down from that midline. That's still 15. The midline is still 11. That does not change. My period is still 3, which means my b value is 2 pi over 3. Now, traditionally, sine starts at 0, goes up, then back down to its min, then back to the midline. I'm doing the reflection of that. I'm starting by going down, which means I need a negative on my a value because that's the graph I'm looking at. Now my c value, well, I traditionally start at 0, but I'm now starting at 2.25 to the right. So my c value needs to be negative 2.25. Awesome. Hopefully that makes sense. But let's talk about another possibility. Again, I really want you to learn from this video. I could start right here, go up, down, and then back to my midline. That would be another sinusoidal graph. So once again, my amplitude is still 15. Again, I'm still 15 feet from the midline, up and down. My midline is still 11. My b value is still 2 pi over 3 because I can't change the fact that my period is 3 seconds. But again, now I'm going up first, which is traditionally what sine does, so I do not need a negative on that a value. And my c value is starting right here at 0.75 to the right, so that's going to be a negative 0.75. So again, another set of values if you were asked for a sine function. So be very, very careful. All right, now let's move on to part C. There's going to be 2 parts here in section C. The first is actual multiple choice. What they're going to do is they're going to have you look a specific section of the graph. In this case, they're having us look from point F to point G. So they're telling us that F is T1 and G is 2T, not T2. They didn't want to give you those times because that would kind of be a cheat for what you already answered back in the previous question. But they're basically telling you look from F to G. And on that interval, T1 to T2, F to G, which of the following is true about the function? Now, I don't know why I had a W here. I'm so sorry. That should obviously say that this is the distance. Okay, now, to answer this question, I like to go back to the graph. They're clearly telling us to look from F to G. So there's F to G. Now, what we're talking about is what are the outputs doing? Well, first thing I notice is that the outputs are decreasing. They go from 26 to 11. The outputs are clearly decreasing. And they're all positive. 26 to 11, yes, it's going down, but they're all positive values. So we're positive and we're decreasing. So from F to G, we're positive and decreasing. That's going to be choice B. But be careful. I don't know which section of the graph they're going to ask about on this year's exam. They could ask about K to P. That would be increasing. My outputs are increasing from 11 to 26, and they're also positive. Now they could, well, I doubt they would actually do this for this type of problem, but they could ask you about G to J. Now here, the values are decreasing from 11 to negative 4, but they're half positive and half negative. Some of them are positive, like 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Zero's in there as well, which is neither positive or negative, and there's also some negative outputs in there as well. So based on how I created this problem, I don't think they would ask you about G to J, because then they'd have to change the answers to, oh, some are positive, some are negative, but they're all decreasing. But you never know what could happen, so be prepared. All right, then finally, question C part 2 is going to say, all right, in the previous part, you described what the outputs are doing. Now describe how the rate of change is changing on this interval. And again, I don't know why I have a W here. I'm so sorry. Should be a D. That's how we define the function. Or actually, we used H. Boy, I'm really off. Should be an H there. Okay, to describe how the rate of changing is changing on that same interval. So again, they're going to keep you looking at that same interval. For our particular problem, that was F to G. Now, what do I notice about the rates of change? Well, first off, I notice that the rates of change are negative. How do I know they're negative? Because if I think about a rate of change at any point on that interval, my rate of change is going to be negative. They all have negative rates of change. But I also know that it's concave down, which means those rates of change are decreasing. Concave down. The rates of change are decreasing. So we have decreasing rates of change. Now again, think about those negative rates of change. They're starting off negative, but a little bit of a slower negative. Then they're picking up pace. They're becoming more and more and more negative. So my rate of change is going down because it's becoming more and more and more and more negative. So again, you can actually see in the graph that it's concave down, and that's going to create rates of change that are decreasing. So this is not a multiple choice question. This is a writing question. So you'd actually write, the rates of change are negative and they're changing at a decreasing rate because the graph is concave down. But again, you might be asked about a different section of the graph. So what if you were asked about this section of the graph? Well, now the rates of change are positive. The rates of change are getting positive. Now they're also concave down though, right? So the rates of change are positive, yet they're still decreasing because they're becoming less and less positive. Early on, they have a pretty big rates of change, and then they start to level off, and the rates of change gets less and less and less. But again, it's still decreasing. So we actually see that we could be concave down in two different ways. From F to G, we're concave down, where we're becoming more and more negative. But when you become more and more negative, your rates of change are still going down. But we also see from K to P, where our rates of change are positive, but they're decreasing in the sense that they're becoming less and less positive. They're getting closer and closer to zero. So hopefully that makes sense. And then one more, just to kind of make sure we get a full gambit here. If we were looking from G to J, we would say that our rates of change are negative, again, because it's decreasing over that interval. But because we're concave up, the rates of change are increasing. They're all negative, but they're becoming less and less negative. And when you have a rate of change that's becoming less and less negative, that actually means the rates of change are getting bigger in terms of, numerical number order. When you become less and less negative, your rates of change are increasing, which is why we see that we're concave up. Just remember, concave up means your rates of change are increasing. Concave down means your rates of change are decreasing. All right, that's exactly what the third FRQ is going to look like. Again, it's not going to be this exact same promise. If it is, it's going to be crazy. That'd be mind-boggling. But it's going to be very similar to exactly how the questions are asked and what you need to do to solve it. So hopefully this video helped you.